So today I want to talk about a function that's closely related to the hypergeometric function, called conjugate hypergeometric function. It's usually denoted by 1f1 alpha beta z. You notice that unlike the hypergeometric function, 2f1 function alpha beta z has b parameters and some independent variable z. This is a function of two parameters and z will show how these two things are related to each other because you get the one from the other. But because you get the one from the other, you can't get more or less everything about the one from the other. Series representation, integral representation, properties of the differential equation, etc. They all kind of follow from one from the other. And I want to use it as an example of the utility of this hypergeometric function. Okay. I'll also give another integral representation for this. Remember, hypergeometric function is a function that is a solution of the hypergeometric equation with a second order differential equation. So it has two linearly independent solutions. We wrote down the integral representation for the one there the last time. I'm going to show you how, starting from the integral representation that we started off with, picking a different contour will generate a linearly independent solution for us. So that will give another integral representation. And in setting up that integral representation, I'll make use of something called the hypergeometric series, which generalizes the geometric series that you're all familiar with from high school. And I'll show you how this function here is really related to many functions that you're already familiar with. And really all it does, all it takes is just tweaking these parameters. Alpha, beta, and gamma. Okay, so we'll explore a little bit of that today. And this will set us up once we know the confluent hypergeometric function. This will set us up to solve the hypergeometric problem. Okay. Right. So I want to illustrate how a different choice of contour in the integral representation for the hypergeometric function will generate another integral representation. So, toward that end, start by noting that the boundary term when we did our integration by parts falls to the function of the integral kernel and the complementary function really is a function of t. There's some factors that I don't really care about, but what I do care about is where this thing vanishes. Because remember, our constraint on generating this integral representation was that the equation for z was as simple as or simpler than the equation for u, and the boundary terms vanished. And the boundary terms vanished if I was doing the integration on a closed contour, because there's no boundaries, the boundary term vanishes, or if I arranged for this boundary term to vanish at the endpoints. Okay, so this thing was proportional to t to the alpha minus gamma plus 1 times t minus 1 to the gamma minus beta times z minus t to minus alpha minus 1. So notice that this thing vanishes when t equals 0 and when t equals 1. Right? So when these terms vanish, u goes to 0. Right? Provided that the real part of alpha is bigger than the real part of gamma minus 1, and the real part of gamma is bigger than the real part of beta. So let's assume that this is the case and see where this takes us. So if this is the case that the real part of alpha is bigger than the real part of gamma minus 1, the real part of gamma is bigger than the real part of beta, then I know that this boundary term is going to vanish when t equals 0 and it's going to vanish when t equals 1. So I can consider a contour that starts at t equals 0 and ends at t equals 1. Okay, so we'll take our contour. From t equals 0 to t equals 1, then our solution W of Z can be written as some constant, which we'll choose just now, the integral from 0 to 1 of Z minus T to the minus alpha times T to the alpha minus gamma times 1 minus T to gamma minus beta minus 1. And if I take out the factor of Z here, then that Z is independent of the integral, so I can pull it out, and that gives me 1 minus T over Z. By assuming that this T over Z factor is less than 1, within the radius of convergence, to make an expansion for this. So this is C tilde times Z to the minus alpha, integral from 0 to 1 minus T over Z to minus alpha, gamma, 1 minus T, gamma minus beta minus 1, dt. I'm going to make a Taylor expansion. We'll make a Taylor expansion in T over Z, expand this function. And I'm going to use the power series expansion, which you're probably not familiar with, but I'll elaborate on it a little bit just now. So Z minus alpha integral from 0 to 1. So from n equals 0 to infinity of gamma alpha plus n. I'll explain in a little bit where this series comes from. Leave me for a moment. So what I've done here is I've made a Taylor expansion in of 1 minus T over Z to the minus alpha. This will be an expansion in T over Z. I've then pulled out anything that is independent of the T's outside of the integral, and I've left an integral with respect to T, and all of the stuff that depends on N, but it's not depending on T, so they're coefficient here. And then this overall multiplicative factor out here. This is really a binomial series expansion, the Taylor series expansion. Start this like this, and you'll see that the coefficients are generalization of the n choose k. This case alpha choose n. Okay. If you remember when you first learned about the binomial series expansion for something like that, you had an n factorial over k factorial, sorry, k factorial over n factorial times n minus k factorial. So gamma function generalizes as a factorial function. This is a generalization. Come back to it in a little. Okay. But the point is that I now have everything split off in n, and then some things that are split off in t. In here, I want to make change of variables. From t 1 over t, in which case the integral becomes integral from 0 to 1. So the integral from 1 to infinity, t to minus alpha minus n minus 1 plus beta times t minus 1 to gamma minus beta minus 1 dt, which you will hopefully recall is one of the integral representations that we gave for the beta function. So I can write this thing as gamma of alpha plus n plus 1 minus gamma, gamma beta divided by gamma of alpha plus n plus 1 minus beta. So this is of the form gamma of something times gamma of something else over gamma of those two somethings. So I can use this then in our integral representation for the solution of the hypergeometric equation. So this recall is the solution of hypergeometric equation. And I can write then that W of Z is this C tilde times C tilde over gamma of alpha times gamma of gamma minus beta times Z minus alpha times gamma of 1 minus gamma over gamma of alpha plus 1 minus beta times the function of alpha minus gamma plus 1 beta plus 1 argument 1 over z such. And then if I choose this integration constant, so firstly these guys cancel off. And if I choose the integration constant c tilde to be precisely 1 over this factor, then gamma alpha plus 1 beta over gamma of gamma plus beta times gamma alpha plus 1 minus gamma. And my solution of the hypergeometric equation is nothing but z minus alpha minus 2f1 of alpha, alpha minus gamma plus 1, alpha minus beta plus 1, argument of z, which is a linearly independent solution to the hypergeometric equation. If you remember the solutions that I wrote down just of the hypergeometric equation, they had one piece that went like 2f1, then one piece that went like z to the minus something, or z to the minus alpha, 2f1 or some other arguments. Well, this is where that stuff comes from, right? But written down in terms of the integral representation. So we picked the general integral representation, and I said you have to choose using the strategy that we formulated of thinking of the differential equation as an operator. And then I said you can write down this equation with some general integration contour, and you have some restriction that how you choose that integration contour. So if you pick an integration contour appropriately, you can generate different integral representations. I showed you one integral representation already. Here's a second one. And in fact, that second one allows us to write down a linearly independent solution of the hypergeometric equation. Okay. In doing this, in particular, this step, I made use of the following series representation for the hypergeometric. Namely, that's 2f1 of alpha, beta, gamma, z, and be expanded in the series gamma of gamma over gamma of alpha and gamma beta times the sum from n equals 0 to infinity of gamma of alpha plus n, gamma of beta plus n, over gamma of n plus 1 times gamma of little gamma plus n, all multiplying z squared. This is in some sense the canonical expansion, series expansion for the hypergeometric function, and it's called the hypergeometric series. Why is it called a hypergeometric series? It's called a hypergeometric series because it generalizes the standard series representation of geometric function. So this generalizes the geometric series. Let me show you how. You see how? We have to tune these parameters. So I'm going to pick alpha equal to 1 and beta and gamma. I'm going to set equal to each other, and I'm just going to call both of them beta. Right. So I'm going to pick alpha equal to 1 and gamma equal to beta. In which case, series representation for 2f1 of 1 beta, beta, Z is gamma of beta over gamma of 1 times gamma of beta times sum from n equals 0 to infinity plus gamma of 1 plus 1 is 2, gamma of beta plus n over gamma of n plus 1 over gamma of beta plus n times z to the n. Sorry, that should be 1 plus n. Okay, now a whole bunch of things cancel. These cancel, this is just equal to 1. These cancel, and these cancel. In other words, this is just the sum. This is just the sum from n equals 0 to infinity z to the n, which is 1 over 1 minus z minus 1. So this is what I mean by the fact that this series generalizes the geometric series. Okay, the geometric series we call was nothing but Taylor expression of 1 minus z to the minus 1. In fact, more generally, 2f1 of alpha beta z is sum of n equals 0 infinity of gamma of alpha plus n over gamma of alpha, gamma of n plus 1 z to the n, which is the series expansion of 1 minus z to minus 1, which is where that series expansion that I used earlier comes from. In fact, by tuning the parameters of the hypergeometric function appropriately, we can show that many of the elementary functions that you're familiar with and that occur quite frequently in physics and mathematics can be expressed in terms of the hypergeometric function. As an exercise, I would like you to show two things in the same way that we've just done for the hypergeometric function. Sorry, in the same way that we've just talked about the geometric series, I would like to show that 2f1 of a half, 3 halves argument z squared is nothing but half sine of z over z. So in this case, the inverse sine of z can be expressed as a particular hypergeometric function z. And 2f1 of 1, 1, 2 with argument minus z is nothing but log of 1 plus z. Logarithm can also be expressed in terms of the hypergeometric solution. Okay. And in fact, even though you can express a lot of the standard elementary functions in mathematics and physics in terms of the hypergeometric function that you get parameters of property, more importantly, you can express non-elementary functions in mathematics and physics in terms of the hypergeometric, or manipulating the geometric functions. These include things like the Jacobi function, Gigapower polynomials, Legendre functions, etc. However, the one that I want to pay attention to is something called confluent hypergeometric function. The confluent hypergeometric function I would like to focus on because it makes an appearance in the solution of the hypergeometric, okay, which is what we want to solve.
Yeah.
Yes.
So when we have this 2 at 1 we get it as a we have that series expansion in Z to the end. Right?
Yes.
So when n equals 0 to infinity, Z to the power.
Yes.
So this series is the only convergence when Z is like mod Z is within 0.
Yes.
But when we made that expansion of like we had 1 minus t over Z to the power something and we expanded it in terms of gamma functions and hence.
Yes.
We said that absolute of t over Z is less than 1. So that would imply that mod Z is greater than mod t. But t goes from 0 to 1. So that should be greater than 1. Yeah, right there. So we have 1 minus t over Z to the power minus s, right? So we assume that t over Z, absolute of t over Z should be less than 1.
In there.
After this, just like when you have the expansion. Right here. Right at the top.
Okay, yeah.
So we went from that step to that step, and we have got 3 gamma functions, and then t to the power n as well, and z 1 over z to the power n.
Yes.
So here we are seeing that e over z, like we were able to make this expansion because e over z is less than 1. So that means z is greater than 1, right? And then that integral over t, it goes from 0 to 1. So z is more than t, so z is greater than 1. But then we got the series, which is only
very good. Okay, so t goes from 0 to 1. All I need is z to be bigger than t. Okay, so the only place that becomes a problem is at 1, specifically at 1. So as long as I'm within that range, everything is fine. So it's what happens at t equals 1. That's the issue.
But
This is a sum of t.
But then at the end you don't have any t. That is why I say so.
Yeah. So okay. So that's a very good point. Which is where does this? What values of z are all of these things relative? So I should have made a point about this, and we didn't in fact say anything about. What the z dependence of the function is. Right? So the key to all of this, in fact, comes with the observation that I haven't actually put any bounds on alpha in this step. Right? I'm just taking it as a parameter. Now that parameter could be an integer, it could be a non-integer, it could be a fraction. Okay? But you realize that if it is, then I really have to be careful about this factor of alpha. Because what it means is that I have possibly something like 1 square root of this thing involving complex numbers, z. Because I also didn't tell you anything about z being real. Which means that I have a branch structure that I need to take into account with this factor. Okay. Which bounds, in fact, it bounds what values z can take. Okay. which actually accounts for what you've just read. So let me expand on this a little bit. As an aside, important aside, let's go to questions like this. Notice the following: 1 minus tz to the minus alpha has 2 branch points. Branch points at okay, so I'm just focusing on 1 minus tz, but the same is true of 1 minus t over z. Okay. Except that in our general integral representation, this factor here is what we encounter, and we make a change of variables to we make a change of variables that brings it to the form 1 minus t over z. So this factor here has 3 branch points that z1 equals 1 over t, and then z2 equals, let's say, infinity. Has 2 branch points at z1 equals 1 over t, and z2 equals infinity. The integral runs from t equals 0 to t equals 1 in our general integral representation. But the integral runs from t equals 0 to t equals 1. And z1, which is some number that can go between 0 and infinity, when t is 1, this is 1. Sorry, not 0 and infinity, 1 and infinity. So since t goes between 0 and 1, z1 is some number that goes between 1 and infinity. And so in setting up this integral, I have to take a branch cut when I set up the contour of the integration. I have to take a branch cut that goes from z equals 1 to z equals 1. And then that will tell me when the integral is well behaved, what values of z the integral will well behave for. In which case, integral is well behaved whenever 0 is less than the argument of 1 minus z. So whenever the argument of 1 minus z is between 0 and 1. So Vincent, you can translate this statement here into when that series converges. It wasn't mentioned in that statement, but thank you for raising it. Okay. So if you go back to the hypergeometric equation, you'll recall that the hypergeometric equation had a leading term that was second order derivatives. Right? The coefficient of that term was z times z minus 1. This tells us what the singularity structure of the equation is. In fact, the hypergeometric equation has 2 regular singular points where that coefficient vanishes. In other words, when z equals 0 or z equals 1. So note that the hypergeometric equation as regular singular points. When z times 1 minus z equals 0, in other words, z equals 0 or z equals 1. And then I have two regular singular points. And mathematically, this is fine. You get to deal with these two regular singular points as you wish. In physical problems, so my claim is that the hypergeometric equation and its relatives show up in actual physical problems, like the hydrogen atom. Right? The key thing about the hydrogen atom and solving Newtonian gravity, for example, is that you're dealing with central potential. Something that goes like 1 over r, which means that there's an actual singularity at the source of the field. So at the source of the gravitational field, at the source of the electric field, there's a singularity. Those one that 1 over r factor that way just goes to 0. So there's really only one physical singularity. There are two regular singular points in the differential equation, z equals 0, z equals 1. There's only one physical singularity. So what do you do with this thing in z equals 1? What you do, the way to accommodate that is to push the z equals 1 singularity out to infinity. Right? How many of you are doing the extreme gravity module thing? Let's do it. So this is kind of the inverse of the Penrose transformation. It brings infinity out to into some finite point. In this case, we want to take the infinity that shows up as z equals 1 and push it out to infinity. Sorry, I used infinity in two different ways there. You want to take the singularity at z equals 1 and you want to push it out to infinity. Okay, so it is in some sense, in a mathematical sense, it's the opposite of Penrose transformation in that sense, in the context of black holes. So we need to in technically only some physical problems. For example, gravity. In essential potential problem. The only physical singularity is x z equals at the order. So to accommodate this, we have to send the singularity at z equals 1 out to infinity. The way we do this is by changing variables from z to, let's say, r times z, and then setting that parameter r out to infinity. Okay. So we can push the other singularity out to infinity by rescaling z to, let's say, x equal to r times z, where this r is a parameter that we get to play with to tune this parameter. And you can see, again, for those of you doing the other module, you can see that this is something like a conformal transformation. Okay, what Penrose transformation does. by rescaling z to that and letting r go to infinity. So if we do this, so we set x equal to r times z, plug it back into our differential equations, basically just check the derivatives and use the chain rule. The hypergeometric equation becomes d2w by dx squared plus gamma over x plus 1 minus gamma plus alpha plus beta over x minus r times dw dx plus alpha over beta, sorry, alpha times beta over x times x minus r times w. So now if I send r to infinity, remember my strategy is first rescale, then send r to infinity. So as r goes to infinity, this equation becomes a first order equation for the derivative of w. That equation is w prime plus gamma over x w prime equals 0. So again, this is a first order equation for w prime. The prime is u by dx. Well, not only is it the first order equation, it's also separable, and I can solve it. Just solve for w prime and integrate to get the equation for w. But if you think about it, this is actually quite a naive way of taking that limit, and the differential equation is more or less trivial, which means that the solution is more or less trivial. So this rescaling by setting z at the singular point at z equals 1 out to infinity is a little too naive. We've thrown away some information. And what we need to do is think a little bit more carefully about how we send z to infinity. And in fact, what we have to do is there are in fact 3 singular points in this differential equation. There's the one at z equals 0, z equals 1, and then there is one already at z equals infinity. So what we've done here is we've taken the one at z equals 1 and pushed it out to infinity and muddled up the waters at infinity. Okay. So what we need to do is think a little bit about how we do this rescaling. And the way we do it is to simultaneously take one of the parameters. Remember our option square 1 has 3 parameters: alpha, beta, and gamma, and it's a function of z. It's symmetric in alpha and beta, you would point. Right? So it doesn't matter what I do with alpha or beta as long as I pick one. If I do it with the other one, you can say answer. So I'm going to pick beta. Right? And what I'm going to do is simultaneously take beta to infinity. Right? So this is an example of what physicists call a double scaling. So to get non-trivial solutions without non-trivial, we simultaneously scale beta, and actually also do this with alpha, to so here as we scale z to rz, okay, and I want to take r to infinity. So the way I do this is to simultaneously set beta equal to r, and then take r to infinity. So if I do that, my differential equation becomes d2w by dr squared, sorry, dx squared, plus gamma over x minus 1 times dw by dx minus alpha over x times w equals 0. Or equivalently, if I put everything z again, or rather, I change my variable back to z by just renaming it and multiply through by z. Z d2w by dz squared plus gamma minus z dw by dz minus alpha w. So, okay, so what I've done here is I've multiplied through by x, and now this is I've called x z. Yeah.
So here z is still equal to
X. No. So maybe I should do this. I just want to indicate that I'm now talking about complex variables. So everybody gets for x. I just multiply through by x. Okay. In this form, this is called the confluent hypergeometric equation. Because what we've done here as a limit of the hypergeometric equation is we've taken the two singular points, conflated them into one, and pushed them up to infinity. So we've taken two regular singular points, conflated them into one irregular singular point at infinity. Okay. Z equals 0 is still a regular singular point. Again, x equals 0 is regular singular point. Where the coefficient of the leading term vanishes. And solutions of this are called confluent hypergeometric functions. They're sometimes denoted by capital phi. And because we set gamma off to infinity, I've really only got 1, 2 parameters. So this is a function of alpha and gamma. Or another notation similar to the one we've been using is this one. We're going to stick with the 1f1 because I think it's better. Yeah, that's a good place to start. Alright, so on Friday, I will show you two bits. I will show you how we use the fact that we arrived at the functional hypergeometric equation by playing around with the parameters and rescaling Z to derive a series expansion for 1f1 from the series expansion for the hypergeometric function. And then we'll solve the hypergeometric. Okay. Okay, good. Any questions?